In this video lecture, I'm going to explain to you and give you an idea, a very basic and primitive idea of what is meant by the solubility of ionic compounds. So what happens when ionic compounds or any compound that ionizes in aqueous state and is present in the form of ions in aqueous state. So what happens to it? So how do ionic compounds dissolve in water? So these blue molecules, these blue particles are water molecules. So these are water molecules surrounding. So I'm going to take a tiny crystal of an ionic compound, a giant ionic lattice. A giant ionic lattice is going to look something like this. It would have positive ions surrounded by negative ions, and those negative ions would then be attracting positive ions. So a giant ionic lattice for an ionic compound is positive ions attracting negative ions and vice versa. So this is a tiny giant ionic lattice. So I'm going to put this crystal, this tiny crystal, let's say this is NaCl. Let's take the example of NaCl. So I'm going to pick the example of NaCl and write that down. So Na is +1, Cl is -1. So this is a giant ionic lattice of NaCl. So the first thing that I would do is that I'm going to stir this. So I'm going to take a spoon, and we're going to. So there's going to be a spoon, a stirrer, and I'm going to vigorously stir this salt crystal, and I'm going to try and mix it with water molecules. So immediately when I use force and when I start stirring, this ionic lattice is going to break and all the ions are going to separate. Because I'm using force, I'm stirring it with some energy and some force, so the ions would separate and they would dissociate and they would go in different directions. So, and they're going to mix with the water molecules which are present over here. So here, as you can see, as I'm stirring, a few of the positive and negative ions, they're breaking apart from the lattice and they're mixing with the water molecules and they're dissociating. So eventually what would happen is that this entire giant ionic lattice, all the ions would break apart, this ionic lattice would break apart and they will dissociate and they would all go in different directions. So in this next step, you can see that the giant ionic lattice has now broken down and all the ions have separated, they've dissociated, and they're all spread out now, and the water molecules are now in between. So this is what would happen when I stir an ionic compound vigorously in aqueous state. I'm going to try and mix it with water. So this is what happens. All the ions separate and they dissociate. So what you can write is that whenever you dissolve NaCl, and we're taking the example of NaCl, whenever NaCl is aqueous, its ions, its positive and its negative ions, Na+1 and Cl-1, they all dissociate, they separate, and they mix with water. So always remember, and this applies to any ionic compound, whenever it dissolves in water, its ions would dissociate, they would separate, so they wouldn't be together. You're not going to write Na and Cl together. You're going to write them in the dissociated form. Na+1 would be roaming around, floating around separately. Cl-1 would be roaming around, floating around in water in the solution separately. And both ions would be aqueous, but now they're dissociated. Now they're not together, but they're separate, and they've spread out and they've mixed with the water molecules. Now the question that needs to be answered is that once you have stirred and all the lattice has broken down and all the positive and negative ions have now mixed with water, the first thing that they would try to do is that the positive ions would attract negative ions. So this positive ion would start attracting this negative ion. This positive ion would start attracting this negative ion. This negative ion would attract this positive ion. The negative and positive ions would start attracting each other. So all these ions, they would start attracting each other. The positive would attract the negative ions and the negative would attract the positive ions. So these dotted lines are the forces of attraction between these particles once they've been dissolved. So now the question is, why don't the ions get back together again and form the lattice back again? So if you're familiar with NaCl, NaCl is a normal table salt. Once it gets dissolved in water, it doesn't get undissolved. So once NaCl dissolves, you would notice that it doesn't form the lattice back again. The salt crystal can no longer be formed back again, and the reason for that is Although the ions would try to get back together again, they would attract each other, they would all be attracting each other with the force of attraction. But the reason why they're not able to get back together again is because of the water molecules. Remember, we're talking about dilute solutions over here, where water is much greater compared to the ionic compound. So the reason why they're not able to get back together again is because there's so many water molecules between them that the attraction between positive and negative ions is not strong enough to displace all the water molecules. So if this negative ion wants to get close to this positive ion, there would be a force of attraction, but because there's so many water molecules in between, the water molecules will not let them get back together again. So this is the reason why once NaCl dissolves, it does not form the ionic lattice back again. So all these ions, when they get dissociated, they remain dissociated. They're going to remain mixed with water, and their ability to attract each other would decrease because of the water molecules that are coming in between, and they're stopping them from joining back again. So this is the reason why compounds, ionic compounds, whenever you dissolve them, they don't get undissolved on their own. But there are some processes, like the process of crystallization, where the crystal is able to form back again. But the process of crystallization requires that you evaporate some of the water molecules. So if I start getting rid of some of the water molecules, let's say these water molecules over here, they're gone. These water molecules over here are gone. And if I start evaporating and I start getting rid of some of the water molecules, so let's say I'm getting rid of some of the water molecules, now the chances of the positive and negative ions getting back together again, so let's remove a lot of positive and negative. Now, once some of the water molecules have been evaporated and the solution is now more concentrated, now the chances of these ions joining with each other and forming a crystal back again, they would increase, because now nothing is stopping them, nothing is coming in between their way. So they're going to start attracting each other, and they would start sticking with each other, and they would start forming the crystal back again. So this is what happens when crystallization takes place. So whenever crystallization takes place, you evaporate the solution to saturation point, which means you get rid of the water molecules that were in between, that were previously stopping the ions from joining and forming the crystal back again. Once you get rid of some of the water molecules, the chances of the ions sticking together and joining and forming the ionic lattice back again, that significantly increases, and you would notice crystals forming back again. So this is one way of forming the crystals back again. In this lecture, we're now going to study why are some ionic compounds more soluble compared to others. So there's some ionic compounds that dissolve readily, whereas the other ionic compounds that don't dissolve readily. So I've taken two examples. One is NaCl, which is a very, very soluble ionic compound. It dissolves very easily. And the other one is magnesium oxide, which is a very, very insoluble compound that doesn't dissolve readily. Now, one difference that you would notice is, for example, if I stir both compounds vigorously in water, both ions, the ionic lattices would dissociate, and the ions will get spread out and they will mix with water molecules. The same would happen if I use enough force and I vigorously stir this. The lattice of MgO would eventually break and the ions would get spread out and they would mix with water molecules. But then what happens? What happens is that the positive and negative ions would try to attract each other. But since Na is +1 and Cl is -1, for NaCl, the force of attraction would be weaker. So the positive ions and the negative ions would not be attracting each other strongly, so they would not be able to displace the water molecules that are coming in between. So they would try to attract each other, but the water molecules in between, the force of attraction is weaker. But in the case of MgO, now look at Mg. Mg is +2 and O is -2. Now the force of attraction between the positive and the negative ions is much, much stronger compared to NaCl. It's twice as much based on the charge alone. So since the force of attraction is a lot stronger, so +2 would attract -2, this +2 would attract -2, this -2 would be attracting this +2, they would be attracting. So all these ions, they would be strongly attracting each other. And since they are strongly attracting each other, this +2 would be attracting -2. Since they are strongly attracting each other, and the force of attraction is a lot stronger compared to +1 and -1, so here the chances of the crystal reforming and the ionic lattice reforming are much greater. So the ions will get back together. So ions get back together due to stronger attraction and form the lattice back again. So it's very hard to actually dissolve MgO and to make it remain dissolved. So it's never going to happen. The magnesium ions and the O2 minus ions would quickly get back together again, and they're going to reform the lattice that was originally we were trying to dissolve. Whereas NaCl, if you dissolve NaCl, NaCl remains dissolved. So this is one of the reasons that if the force of attraction between ions is very strong, the chances of them dissolving in water would decrease. And if the force of attraction between ions is very weak, the chances of the ions remaining dissolved in the solution or dissolving in the solution would be very high. So we can come up with a very general rule for solubility, which is that if there are smaller charges on ions, which means that they are lesser attractive forces, so the chances of the ions remaining dissolved in water would be greater, so there would be greater solubility. And if there are greater charges on ions, for example, like magnesium and oxygen ions over here, the stronger the attractive forces, the lesser would be the solubility, because ions would try to get back together again to form the lattice back again, so they're not going to remain dissolved in the solution. So they're quickly going to undissolve and reform the lattice that was broken while you were stirring. So the lesser would be the solubility. So this is a very general rule you can apply, but it doesn't. But it's a very general criteria. So what we are going to study next is the solubility table. We're going to be very specific about which compounds are soluble and which compounds are not soluble.